Hello, science students. Today we're doing What is the Future of Earth's Climate? We're doing Activity 6, Using Models to Make Predictions. Complex climate models. If you've seen, studying climate change involves understanding many different factors and how they interact in the complicated Earth systems. Earth's climates are fueled by solar energy and complex interactions between the atmosphere, land, oceans, living things, including humans. Our best hope of understanding how the global temperature changes over time and how we may be affecting it lies in the mathematical climate models that scientists have developed over the past 50 years. Climate models are some of the most complex models in all fields of science, and they have already proven to be useful in simulating past climates. So this diagram shows the evolution of climate models. So in the mid-1970s, we were just thinking about the atmosphere. In the mid-80s, we were including atmosphere and land surfaces in our models of climate. In the early 90s, we added ocean, sea, and ice. And remember, the water can reflect sunlight, or the ice will generally reflect sunlight, and the water will generally absorb that sunlight and then re-radiate it as heat. So ice and water behaved differently. Late 1990s, the atmosphere, land surfaces, ocean, and we added sulfates. Sulfates are put into the air by pollutions and also volcanoes. They help block the sun a bit, but they also can make acid rain. Present day, we've added non-sulfite aerosols, so other types of pollution that make tiny little particles, and the carbon cycle. So where is that carbon? Is it locked up in trees? Is it in the soil? Is it in rocks? Is it in the air? Is it in living things? And then we've also added dynamic vegetation. So is the vegetation absorbing heat? Is it releasing heat? Is it reflecting sunlight? And atmospheric chemistry. Things that are in the atmosphere react with each other and make new kinds of chemicals, new kinds of chemical compounds in the atmosphere. So our models have become more and more sophisticated as we go forward, and probably will continue to become more sophisticated as we really struggle to predict what climate is going to bring in the next decade or 2 or 3 as we try to adapt to climate change. At this point, it's unlikely that we can stop climate change anytime soon. We have to adapt to it, and hopefully we can slow it down. So, time lags in temperature changes. You may remember that the temperature changed pretty quickly after you changed the carbon dioxide levels when you used the models in Activity 4. In the real world, there's a lag between increased carbon dioxide levels and temperature increases. The image shows how carbon dioxide moves throughout the Earth's system. Remember that each source of carbon dioxide is also a sink for carbon dioxide. So what they mean is carbon dioxide can go into the ocean, it can be absorbed by the ocean water, and can hang out there for a while. But as the ocean heats up, or just, it's always releasing CO2. So the ocean is both a source, it can release CO2, especially if it gets hotter, and it can also absorb CO2. Sediments, they can release CO2 as they come up on land and erode away. Or CO2 from small animals in the ocean can fall down and become sediment and hang out in the rock for quite some time. So lots of all these parts can become a source. It can release carbon dioxide, or a sink and can absorb carbon dioxide. Now, all of this stuff in this model cools and heats very slowly. Air, although there's a lot of it, so it probably cools and heats the most rapidly. But the ocean, if you think about having a big pot of water and how long it takes to heat a very large pot of water, think about how long it takes to heat an ocean. Once the ocean heats up, it's going to take a while for it to cool down. Same with land. Land has a lot of mass to it, and it also holds heat very well. Think about like a radiator or something that is designed to hold heat in everyday life. And that's kind of how the Earth acts. So why is there a lag between changes in CO2 levels and temperature? Remember that there are many reservoirs for carbon dioxide. Where can carbon dioxide be stored when the temperature is low? Well, when the temperature is low, you could store carbon dioxide in sediments. You could also store it in the atmosphere. You could store, it might be saved as air bubbles in ice. If it's not too low, you can store carbon dioxide in trees, in the soil, as dead plant material in the soil. The whole deal here is the Earth is really big and takes up a very long time to heat up and a very long time to cool down. So if the atmosphere has more CO2, the Earth is going to hold more heat, but it will take some time to heat up. It'll also take some time to cool down. If we can slow climate change, it will take some time to cool Earth down. Carbon dioxide is also stored in the permafrost. Permafrost is, it's mostly methane stored in the permafrost, but there's also carbon stored in the permafrost. It's frozen soil in places like northern Russia, Alaska. The soil is permanently frozen, and so none of the carbon dioxide, the carbon in that soil can decay, and so it can't be released into the atmosphere. Once we warm that up, the permafrost is starting to melt in Alaska. It's starting to melt in northern Russia. It's going to release carbon dioxide and methane, which is a very potent greenhouse gas. So let's actually talk to a climate scientist here. We're on page 3. Mark Chandler works on climate models. You've used many different models in this unit, just as climate scientists use models to better predict what will happen in the future. How do scientists' models different from the models you've used? How do scientists use their models? The Earth system is very complex, and how can you tell the models are even valid? Mark Chandler is a climate scientist at NASA Goddard Institute for Space Sciences at Columbia University. In the video, he discusses how climate scientists use mathematical climate models to reproduce past climates. So you can test your model by putting in data from climates that were in the past, climates that were millions of years ago. And if the input data produces the climate that you think was there, then your model has some usefulness. Dr. Chandler works on modeling paleoclimates, climates from millions of years ago. He uses computers to run mathematical models of past climates. The computer programs he uses show the results of the mathematical computations visually so he can see where and how Earth's climates have changed in the past. So he works with a lot of maps. Not very long ago, weather forecasts were rarely accurate beyond a day. With faster computers, weather forecasters were able to take into account many more factors. And now 7-day forecasts are pretty accurate most of the time. The same computing speed that has brought better weather forecasting is also bringing better climate modeling. We have faster computers. Just think about how much better video games have gotten in the last 40 years. Think back to Pong, if you know what that is. And now we have virtual reality and all kinds of cool stuff going on. We can play people in other countries simultaneously in the same game. It's pretty cool. And so that same evolution of technology has happened in climate modeling. More factors can be considered at the same time, making the models more likely to be accurate. So we can develop better models, just like weather forecasting. We have better technology, just like video games. And so we're going to listen to Mark Chandler for a few minutes, talk about how he uses models.
My name is Mark Chandler, and I'm a scientist at NASA's Goddard Institute for Space Studies and at Columbia University in the city of New York. The Goddard Institute for Space Studies is one of NASA's primary climate modeling centers. One of the main focuses of our institute is to build large computer models that simulate all of the Earth's climate systems. So a computer climate model is, in some sense, an encyclopedia of the Earth written in computer code. We're really trying to simulate everything in the Earth system. I mean, that's the eventual goal. In our case, the result of our computer program is a simulation of the Earth, which can be visualized as well in terms of maps of the Earth's temperature, maps of the Earth's precipitation fields, and 900 other potential variables as well. The models that you use in your curriculum are also computer programs, but they tend to be fairly simple programs that are intended to illustrate the relationship between one or two input variables and one or two output variables, because the purpose of those models is to illustrate very specific points. Our models are intended to actually simulate the entire Earth system in all of its complexity. So why do we build these complex models then? We are very confident that we understand the basics, and we really don't even need the models to actually have a basic understanding of the fact that greenhouse gases actually trap heat in the atmosphere, and that if we're putting a lot more greenhouse gases into the atmosphere, they're going to trap a lot more heat and the planet's going to warm up. By simulating things like the ice ages or times in the way past that were much warmer than today, we can actually get a handle on whether or not these climate models are realistic enough to use to predict the future. If we understand how the Earth has changed in the past when things like greenhouse gases actually were changing naturally, then we feel that we'll have a much better understanding as to how the Earth will change in the future when greenhouse gases are changing naturally plus changing due to the fact that humans are putting in lots more of these various types of compounds into the atmosphere. It's not to say that the Earth has never experienced these huge levels of greenhouse gases. The Earth has had many times in its past when it's been more greenhouse gases in much warmer climates. But it's never happened on such a rapid pace as it's happening right now. Within 100 years, we're going to put enough greenhouse gases into the atmosphere such that we'll be at levels that the Earth hasn't experienced in 50 million years. That's a scary prospect. So our confidence in the models is based on how well it matches paleoclimate in terms of how well they respond to very large changes in greenhouse gases. But another major way of testing the models is how well they do for what we would call modern climate, but what we really mean by modern climate is, say, the climate from the late 19th century up to the present day. The climate models are actually extremely good at reproducing the types of climate changes that have occurred over the last century or century and a half, particularly in the areas of temperature. We need a lot better understanding, probably from climate models, as to how all the details work. And institutes like ours will continue to try to improve the models to make them more capable of getting the details correct. We'll use the climate models to try to give us better information on exactly what is going to occur. And so what do we need to adapt to? But let's also, let's not waste another 30 years because we have to stop this before it gets to the point where nobody can adapt to it.
So what Dr. Chandler is talking about is that we need models to predict exactly how much the Earth might warm up, where there's going to be more precipitation, where there'll be less precipitation. And those models are really important for doing long-term planning in communities. We just did the flood module. We understand communities need to know where their 100-year floodplain is, where their 500-year floodplain is, and those might be expanding as precipitation patterns change with climate change. Cities and countries need to know about how their agriculture might need to change to keep up with changing temperatures. Places that deal with snow, like ski centers or even cities that have to snowplow, they need to know how much snow might fall or not fall to plan snow plowing. Or if you run a business that depends on snow and snow is going to disappear, then you need to know that ahead of time so you can change your business model. Maybe you'll go from being a ski hill to a mountain biking center. So Mark said models are not really necessary to understand the very basics of climate change. We know that we're putting more greenhouse gases in the atmosphere and the Earth is heating up. That's pretty simple. But to get the details on climate change, we need to very sophisticated models that take in what he said is up to 900 variables. So you can choose yes or no to question 2. I chose no just to be a bit of the devil's advocate. For a basic understanding, we know that my claim was no for a very basic understanding. We know that greenhouse gases are causing the Earth to warm and that we're putting more of those gases into the atmosphere. We don't need to be able to change, we don't need a sophisticated model to know that we need to change our actions and stop putting greenhouse gases if we don't want it to warm up anymore. You could also write yes to this answer. Yes, we need to know in order to do long-term planning for cities and countries who really need to think about where should we put houses? Where is the floodplain going to be? In the rivers, if we get more precipitation, where is it going to snow? Where is it going to stop snowing? Where might it start snowing? What kind of trees should we plant? That's a big question here in the Midwest because a lot of our trees are dying as the climate shifts. And we're asking ourselves, okay, if the climate's going to get warmer, maybe how much warmer is it going to be and what kinds of trees will grow in those conditions? And if our precipitation is changing, how might agriculture, how might what we grow need to change as well? How can you and scientists tell that a model is good? What kinds of tests can you run to assess the validity of the model? Well, what Dr. Chandler does is he takes the input data from climates of long ago, and he sees if the output, the climate that's created in the model, matches the climate we think occurred millions of years ago. He can also do that with modern climate data. Put in some of the CO2, some of the temperature and rainfall data from that particular time, and then use it to forecast how the climate might change in 10 or 20 years. And if the data from the model matches the data that actually happened, say he put in data from 1910 to predict what the climate was going to be in 1920 or 1930, and he got information from his model that matched the actual climate in 1920 or 1930, then his model seems to be pretty valid. If you put in the input data, like the amount of greenhouse gases, the current temperature of the ocean, the amount of precipitation, and you can use that to predict a climate that has already existed, your model's doing pretty well. It's basically, you can kind of check your answer because the answers exist for past climates, but we can't do that for climates that haven't happened yet. We don't know for sure what the climate's going to be in 2050. So we're using our data to predict past climates, and then we're going forward and putting in today's data to predict the climate of 2050, 2080, 2100. So societal effects. How is climate change going to affect all the people who live in the world? Having used our models, what do they tell you about Earth's temperature might change in years to come? Scientists use climate models to make predictions. They set up different tests that look at predicted future emissions of greenhouse gases. They build models to take into account expected changes in emissions and fossil fuel usage to try to better predict the effects of humans' actions on the temperature. These factors contribute to some of the uncertainty in climate predictions. Despite the uncertainties, all scientific models show that the Earth will warm in the next century. Basically, what that means is we don't know exactly how much it's going to warm because we don't know exactly how much CO2 and methane we're going to keep pumping into the atmosphere. Obviously, if we keep putting in lots of CO2 and methane, we're going to warm much faster than if we try to slow that process down. Faced with warnings, the public's natural response is to ask scientists for definitive guidance. Scientists cannot say exactly what's going to happen in every region of the world at a specific time, but they can tell you about trends. For example, when we looked at the flooding module, they can show you that the Midwest has more precipitation in the last several decades. They can't tell you how much it's going to rain tomorrow or even next year, but they can tell that on average, we'll get more rain and we'll probably get more rain all at once. Those extreme rainfall events, like where you get 8 inches in 2 days, those will happen more often. It's not solely up to scientists to find solutions to problems. A scientist's job is to learn how the system works, in this case, Earth's system. It's the job of society to be well educated about the science so they can make informed decisions to solve problems. For example, are electric cars a good idea? How should we generate our power as a city? The Earth's system is complex. We keep adding more variables to the model and it keeps getting better, but there's still variables we haven't even thought about. There's so many different factors that influences Earth's temperature, but the models are getting better at simulating past climates. Until a decade or so ago, they weren't putting in permafrost into the models. When permafrost melts, it releases lots of methane, and that methane can really speed up climate change quick. So as we keep thinking about models, and they weren't also calculating that as the oceans warm, water expands just a little bit when you heat it. And even 1 or 2 degrees, which isn't a big deal if it's your bathtub, but if it's the ocean, the seas are going to rise just a little bit as the water warms, even if we don't melt any ice. That's something that's gone in the model in the past decade or two. So we'll keep thinking of things that will make our models better. The science will always be incomplete. We'll always be improving our models and figuring out exactly how much carbon dioxide we're going to add to the air. But waiting for absolute certainty would mean waiting forever. Because as we learned, science is always a little bit uncertain. We can't ever predict the future perfectly. How can scientists be sure that the Earth is getting warmer when they are not completely certain about what's going to happen to Earth's temperature in the future? There's some uncertainty in the models because we don't know the carbon dioxide and methane variables, which depend on how smart we get as a human society and how much CO2 and methane we keep adding to the atmosphere. Another way to think about it is if you go to a basketball game, you can make a pretty good prediction about what's going to happen. You don't always know which team is going to win, but there will be dribbling and passing and dunking, and people will be running up and down the court. The crowd will probably be cheering, and the score will be in probably the 80 to 100 range. Just because you don't know who's going to win doesn't make it not fun to go to the basketball game. You can still predict what's going to happen when you get there. It's going to be a typical basketball game. And that's how scientists look at the Earth too. We know it's going to rain. We know it's going to get hotter. We know some places are going to get drier. Exactly what the outcome is, we don't know, but we still need to pay attention. So page 5 and 6, we're going to save for part 2. We're going to look at this cool, complicated graph about the temperature in paleoclimates long ago, millions of years ago, and current temperature. Thanks for watching. I'll see you in part 2. This is activity 6 in What is the Future of Earth's Climate? Dr. B signing off.